Hello everyone, welcome to the course on concepts of engineering mathematics. Okay, so this is a short course in which we will see some important and frequently used concepts of mathematics which are utilized for solving several engineering application related problems. Okay, so we will begin our discussion with determinants and matrices. So let us see what are determinants and matrices and how the operations are done using them. Okay. So first, let us see what are determinants and how the calculations are performed using them. Okay. So determinants. So determinants basically are a way to represent data and to solve them. In fact, determinant is a scalar value and it is calculated out of matrix. Okay, so this is also a way of representing the data in the form of an array containing rows and columns. Okay, so it is array of or say array containing rows and columns, rows and columns, and we have a symbol to represent data, sorry, determinants. So determinants are represented as say like this. Okay, so where these bars basically are used to include the rows and columns, and in determinants the number of rows are equal to the number of columns. Okay, so number of rows and columns are equal. Okay. And when we solve the determinant or expand it, we get a scalar value. Okay, so expansion of determinant results in a scalar value. So results in a scalar value. Okay. So let us see an example that how determinant is represented. Okay. So this is generally for now. Let us take a matrix A. We'll see what we mean by matrices and how are they represented. But for now, let us say we have a square matrix A. So we have matrix A. We will see what we mean by square matrix and even what is meant by matrix. So suppose we have A, B, C, and A, B, C, L, M, N, and say J, K, L. Okay. Or we can put anything. These are arbitrary alphabets or values which we are placing just to indicate the representation of determinants. Okay, so this is a square matrix, and for better understanding, a square matrix means a matrix where number of rows and number of columns are equal. And we have seen that in case of determinants, the number of rows and columns must be equal. Okay, so its determinant will then be this will be like represented like this. Okay, so this bracket type of symbol will be replaced by vertical bars, and we will place the values like this. Okay, so like this, a determinant is represented. Okay, so and upon expansion, we will get a scalar value. So we will see in a while how the determinants are expanded. Okay, so before that, let us see what we mean by a minor, because we will be needing the minors for expanding the determinants. Okay, so and as I mentioned, the symbol Aij. Okay, so see, this is Aij. Okay, so here I represents the row, number of row. Okay, so these are rows. Okay, and in this direction we have, let me use some other color. So say these are the rows, and here we have columns. Okay. Means this was like this, and these are rows, and these are the columns. Okay. Like this, these are columns. So I represents the row and J represents the column. So J is column. So we can in fact tell the position of particular element. Say I say A11. So that means the element present in the determinant at in the first row and in the first column. Similarly, A13 will mean element in row number 1 and column number 3. Okay, so we can in fact get the particular positions of elements like that. Okay, for example, say we have a determinant, say B as 1, 2, 3, 4, 5, 6, 7, 8, 9, like this. Okay, so in this case, if we say if we want to know that what is B11, then here 1 represents the row, first one, and second one represents the column. So in the first row and first column we have 1. Okay, similarly, if we say B3, 2, then we will first see 3. 3 will be the row number. So in the third row, we will look for second value, which is 2, that represents the column. So in the third row and second column, we have 8. Okay, and so on. So in this way, we can locate various elements. Okay, so now let us see what is meant by minor. Okay, so now minor. So minor of a determinant Aij is again determinant of the particular element value, means that particular determinant expansion after deleting that particular row and column in out of which we are talking. Say minor of A11, if we want to calculate, then we will delete the first row and first column, and after that we will expand the determinant. Okay, so this is nothing but the determinant obtained by here. In fact, we are in sort reducing the dimensions of the determinant. Okay, so the determinant obtained by deleting, obtained by deleting or hiding, say hiding, hiding the row and column, hiding the row or row and column, in fact row and column to which Aij belongs. So for a determinant of uh, order 2 means there will be 2 rows and 2 columns. In that case, the value of determinant is simply found as, so if we have say A, B, C and D, then the expansion of this determinant to find the scalar value is given as this first element is multiplied with the element in second row and second column. Okay, and from this the product of these two elements will be subtracted. Okay, so this will be say AD minus BC. So this will give us the scalar value of this determinant, and this particular operation is known as the expansion of determinant. This is the shortest or means smallest determinant possible that we can expand. After this, if we reduce the order, we will get one by one determinant, which will be a single value, a scalar value. Okay. So in case of this 2 by 2 determinant, this is evaluated by this method. And for higher order determinants, we will now use minus to find the value of determinant. Okay, so we had an example of a matrix. Say, let us write again that we have determinant A. So first let us see how we write the minors. So we have say A, then this A is nothing but say 1, 2, 3, 4, 5, 6 and minus 2, 3, 4. These can be any values, even complex values also. Okay, so here the minor of A23 is given as, so minor of say A, let us say A32. Okay, so we will look for the third row and second column, and then we will delete that particular row and column, and after that the determinant which will be remaining will be the minor of this A32. Okay, so here determinant A has 3 rows and 3 columns. Okay, so in the third row and second column we have to delete here. So if we delete them, what we find, we will be left with a 2 by 2 determinant. So which will be third row deleted and second column deleted. So we have the first column, first row. So 1 and 2 is deleted, so 3, and second row will be there, so 4. Second column has been deleted, so we have 6, and third row is deleted. Okay, so we do not need to write the third row. Okay, so we have this value. Okay, and in a similar manner we can find the other minors also. Okay, so if it were a 4 by 4 determinant or fourth order determinants, then in that case we would have written the remaining 3 rows and 3 columns after deleting the particular one for which we are looking the minor. Okay, so in this way we calculate the minor. Now after this minor, let us see what we mean by cofactor. Okay, so a cofactor is nothing but a minor with its proper sign. Okay, so Now we have cofactor. Okay, so cofactor of A, say Aij. Again, cofactor is nothing but the, as I mentioned, it is the minor with proper sign. So proper sign, how do we calculate? Is given as minus 1 raised to power I plus j into the minor of Aij. Okay. Into minor of Aij. So in this way, the cofactor is given. Now the expansion of determinant will be done using cofactor actually. So their minor will be involved automatically with its proper sign. Okay. So let us see what is cofactor again before proceeding ahead. So like take the same example which we took earlier. So now we will find cofactor of A32 from the above matrix. So this will be minus 1 raised to power I plus j, which is 3 plus 2 into the minor of A32 into minor of A32. And here minus 1 raised to power 5 is nothing but minus 1. So simply let us write this as negative of 1, 3, 4 and 6. Okay. So this gives us the cofactor. So this has now been written with proper sign. Okay. So now the determinant, how is it calculated or how the expansion is done? Let us see. So suppose we have a matrix or a determinant. Let me not use the word matrix frequently. We'll see it later. So determinant expansion simply. Determinant expansion. So how is it done? We can select any row or column. So select any row or column. Okay. Then for that particular row or column, we need to find all the cofactors. Okay. So now find the cofactors of each element in that row or column. Row or column. This can be done using both either the row or column. And after we have found the cofactors, we need to add the product of respective elements with their cofactors. Okay, so say we have selected the first row of a third order determinant. So there in that case, we will have say A11, A12 and A13 as the three elements. Then we need to find the determinant, we need to add the so product of these elements with their cofactors. Means say A11 multiplied by cofactor of A11 plus A12 multiplied by cofactor of A12 plus A13 multiplied by cofactor of A13. Okay, so in this way it can go on. So next step is addition of products of the of all the elements with their respective cofactors. Okay, of all the elements of that row or column with their respective cofactors. Okay. So in this way, the determinant can be expanded. Okay, so let us understand or see these concepts with the help of an example. So it will be much clearer. Okay. Let us do this for fourth order determinant. Okay. So now we will solve an example. Say this is question 1 here. So we have to find, say, determinant A is given as uh, -1, 1, 2, 1. Okay. Then 2, 1, 3, 2, and then 3, 2, -6, 0. Then we have, say, -2, -2, 4, and then -4. Okay. So let us find the value of this determinant. Okay, or let us expand this determinant. So as I mentioned, we now need to select any row or column and then find its respective cofactors. Okay. And then we will add the products of these elements which were of the row which we have selected or column which we have selected with their respective cofactors, and we will add them together. Okay. So let us select the first row itself. So here what will be done? So since I have selected the first row, we will write the element and its product with its cofactor. Okay, so here the cofactor will be -1 raised to power I plus j into the minor of aij. So here our element is a11, say. Okay, so means the element at first row and first column. Okay, so here -1 raised to power I plus j will be -1 raised to power 1 plus 1, which is -1 to power 2. So there will be no change of sign. Means this I plus j simply represent if they are if the sum I plus j is uh, even, then there will be no change of sign. And if these the sum is odd, then there will be -1 raised to power some odd value, which will result in -1 itself. So the sign will get changed. Okay. So here for a11 there will be no change of sign, so -1 will be taken. Okay. Or this minor will be multiplied with 1 only. Okay. So -1 into minor will be, here minor will be, we deleted the first one, first column, then we will have 1, 3, 2, 2, -6, 0, then -2, 4, and -4. Okay, so this is for the first element of the row we selected. Then we will move to the second element, and here we have we need to add. So this will be 2, and since this is the element a12, say, so here -1 raised to power 1 plus 2, that is -1 to power 3, that is -1. So let me directly put minus here. Okay. So we have this minus comes due to the cofactor term. Okay, so cofactor is nothing but -1 to power 1 plus 2 here in this case into the minor of this a12, which will be, delete the first row and second column. So this is 1, 2, 1, 2, -6, 0. This is -2, 4, and -4. And we'll go on like this till we reach the last element of this row. So again we have 3, and this is element number a13. So 1 plus 3 is even, so there will be no change of sign. So +3 into, delete the first row and third column. So we will end with 1, 2, 1, 1, 3, 2, and then -2, 4 and -4. Okay, and again we will have the last element of this row. So -2, and here the sign will get changed because we have -1 raised to power 1 plus 4, that is 5. Okay, first row, fourth column, 1 plus 5 or 4 is 5, so odd value. So this will be minus minus plus 2 into the minor. Okay. So minor is, delete the first row and fourth column. This is 1 2 1 1 3 2 2 -6 and 0. Okay. I have taken this fourth order determinant directly so that we can easily understand here how we can calculate the third order determinant also. Okay, so now we are left with four third order determinants. Okay, means determinants with 3 rows and 3 columns. There are 4 such. Okay, so now for them also we need to do the same. So now here we will do some direct calculations. We have seen that for 2 by 2 determinant, means second order determinant, we simply take the difference of cross multiplied elements. Okay, means say we have a11, a12, a21 and a22. So in that case, what happens? We multiply a11 with a22 and then take the difference of product of a12 and a21. Okay. Like we did here in this example. Okay, where we had, yes, a b c d. Okay, so ad minus bc. We'll do the same in every case. Okay, so now let me solve it further. So here what happens is minus will be as it is and will not expand the determinant here. So -1 means minus only. And now let us take the first row again. So 1, then here again 1 is a11 here for this particular determinant, third order determinant. So -1 raised to power 1 plus 1 even. So I'll not repeat this again and again. We'll consider this now. Okay. So 1 into, now the minor is this 6 6 4. Okay, so let me erase. This will be 6 4 0 minus 4. Okay, so directly taking the values, we have -6 into -4 as plus 24. Then -4 into 0 is 0. Okay. Then the next one will be -2. Okay, it is obvious that negative sign will come. Here the minor is 3 4 2 -4. So the products are 4 3s are -12 and -8. Then if we move ahead, what we have now -2 again, and now this time the product is 0 minus minus plus 12. Okay, 6 2s are 12 and minus will get plus, converted to plus. So this is the expansion of first third order determinant here. Next we have -2 times the second one, which is 1 into, again 6 4s are 24, and then 4 zeros are 0. Then we have at the second place again 2. Is it correct? Yes, this goes like this. So 2, and again we have the product as 4 2s are 8 -8 and -4. Okay, and then we have -2 again, and this becomes 0 plus 6. Okay, and this completes the second one. Similarly, the third one, let me indicate here how we are taking the product so it becomes clear to understand. So we'll now take this one. So this is 1, Now we'll multiply it with its cofactor. We'll automatically considering the signs. Okay, so means we are alternating the signs as we are moving ahead. So this now becomes this 3 into 4 is minus 12 minus this product of these two. Okay, so this will be 4 to some 8, so minus 8. Okay, in this way. Okay. So let me erase from here and let us proceed ahead. So similarly, this is minus 1 and product will be now minus 8 minus 4. Okay. And this will be minus 2 and the product will be 4 minus 3, and at the last we have plus 2 into expansion of this last determinant, which is 1 into 3 zeros are 0 minus plus 12, then minus 1 into 0 minus plus 6 plus 2, okay, into 2 2s are 4 minus 3. Okay. Now solving this, we can get the value of determinant. So let us see what comes next. Okay, so this is a minus sign will be kept as it is. This is 24 and this becomes minus 12 minus 8 becomes minus 20 and 22 is 40. So this is minus plus 40 and then we have 24. Okay, 12 2s are 24. So minus 24. This is the first. Then we have 2 minus 2 into again 24 and 8 4 12. 12 2s are 24. So plus 24. Okay, and then 6 2s are 12. So minus 12. And then we have plus 3 into this is again 20, which is with minus sign, and then 8 4 12. 12 ones are 12 minus plus, so plus 12, and then 4 minus 3 is 1 and this is minus 2. And after that we have plus 2 into 12 minus 6 plus 2. Okay, and again after solving this, further expanding, we have this 24 gets cancelled, so this is minus 40, and here again we have 24 minus 12 is 12, so 36. 36 into 2 is 72, so we have minus 72, and after this we have 12 minus 2 is 10, and 20 plus 20 means minus 20 plus 10 is minus 10. Minus 10 into 3 is minus 30, and then we have 12 minus 6 is 6 plus 2 8. 8 was 16, so this is 16. So this becomes, this value comes out to be minus 126. So in this way the determinants are expanded. So this gives us the answer. So in this way any even higher order determinants can be expanded. So that's why I took directly fourth order determinant, so it covers all third order as well as second. Now let us see some of the facts or properties of determinants which will be very helpful while solving further problems. Okay, so some properties of the determinants. So we will now see properties of determinants. Okay, so there are very fundamental rules for these determinants, that if the first one is very first is the value of a determinants remain unaltered or unchanged if the rows are interchanged into columns or columns are interchanged into rows. Okay, Means this process is known as transpose. Okay. Means rows are converted to columns and columns are converted to rows. Let us see how this happens. So let me first write that the value of determinant remains unchanged. Will not go into the derivation. We can actually prove it also. So let us see. The value of determinant remains unchanged if the rows are transformed to columns and columns to rows. Columns to rows. So what does this mean? That say if we have a determinant A, which is say A1, B1, C1, A2, B2, C2, A3, B3, and C3. So here we have first row as A1, B1, C1, second row is A2, B2, C2, and third row is A3, B3, C3. So if we convert the rows into columns or columns into rows, both means the same thing. So in that case, the determinant value will not change. So this will be same as this A1. Rows are now converted to columns. So A1, B1, C1, and this is A2, B2, C2, and this is now A3, B3, and C3. So you can see that here the rows were A1, B1, C1, which have now become the column. Column wise, we can see A1, B1, C1, A2, B2, C2, and A3, B3, C3. Okay, so this is also called as transposing the determinant, means converting the rows into columns. This transport word or term will be again used in matrices. Okay. So this is an important operation. So this was the very first property. Now the second property is if any two rows are interchanged with each other, or say any two columns are interchanged with each other. Okay. Remember, row will be interchanged with row only, not the column. And in case of columns, one of the columns will be interchanged with other column, not the row. So in that case, the sign of determinant gets reversed, or the determinant changes its sign. So if it is the scalar value which was coming was positive, will then turn to negative, or vice versa. Okay. So if two rows or columns are interchanged, interchanged, the determinant changes its sign. The determinant changes its sign. So how this happens? So say we had a determinant A, which was, let us take the above example again. So A1, B1, C1, and say this is A2, B2, C2, and this is A3, B3, C3. And suppose we interchange the first and second rows with each other. Okay, so in that case, the value will be now. So this becomes now, say this is A2, B2, C2. Okay, so R1 we are interchanging with R2, A2, B2, C2, and this becomes A1, B1, C1. This is A3, B3, C3. This will now result in negative of determinant of A. So the sign gets changed. The scalar value will change its sign. Okay. Also, the symbol delta is used to represent the value of determinants. Okay, so say this was delta, then this becomes minus of delta, minus delta. So this is the second property. Now, next one is related again to the nature of elements. Okay, so the value of the determinant becomes 0 when the conditions, these conditions are achieved, which we will see. That is the value of determinant is 0 if when first case is all the elements of a row or column, whether it be any row or column, if all the elements are 0, then the determinant is 0. Okay, so if all the elements of a row or column are 0. Okay, and also it will be 0 when two of the rows or columns are identical. Means either two rows are identical or two of the columns are identical. Okay. Remember, when in these properties, when we say rows, then we will see the relation between rows only, and if we say column, then we will see the relation between any two columns only. Okay. So if two rows or columns are identical, means they are exactly same. So in that case also, the determinant will have its value as 0. Okay. And one more condition is there when the determinant becomes 0. That is if any of the two rows or any two columns are proportional. Okay. So if two rows or columns are proportional. Okay. So in these cases, the value of determinant becomes 0. Okay. Now, the next property is that if the if any scalar is multiplied to the determinant and it goes inside the determinant, then the scalar gets multiplied to any particular row or column at a time. Okay. So what does this mean? That this can be written as, say we have a determinant A1, B1, C1, A2, B2, C2, A3, B3, C3, C3, like this. And if we multiply this with some scalar, say K, then this gets multiplied to any of the rows or any of the columns. So let us say that this gets multiplied to the first row. Okay. So this is K, sorry, this was B1 and this is C1. Okay. This is now A2, B2, C2. We have now A3, B3 and C3. Okay. So any of the factor or any scalar value when gets multiplied to the determinant, and then in that case it gets multiplied to all the elements of any particular row or column. Okay. So, or in other words, we can say that if the elements of any row or column of the determinant are multiplied by the same number, then the determinant itself gets multiplied that number. Okay. So this was the one next property, and now we have one more, that we can write the determinant in terms of uh, the multiples, fractional multiples, not multiples means we can add the row, any row with other row in with proper proportions. Okay, and in that case, the value of determinant will not get changed. Okay, so what I'm trying to say is, let us see with the help of this example again. So say we have a determinant A1, B1, C1, A2, B2, C2, and A3, B3, C3. Then this is same as writing A1 plus K A2, means we are taking proper proportion or fraction of the second row and adding it to the first one. Okay, so in this way, the value of determinant will not change. Okay. So similarly, B1 plus same fraction. Okay, this will be same, and B2, and again C2, sorry, C1 plus K times C2. Another rows remain same without any alteration. Okay. So at a time we can apply the operations to only any one row or column. Okay, so this was B3 and C3. So in this way, the value of determinant does not change. Okay, so these are some of the important properties which are needed while solving the problems related to determinants. Okay. Now, what is the geometric significance of determinants? Okay. So determinants can be used to find the equation of a line, and also to find the equation of a plane if the coordinates are given. Okay. So now let us see the geometric significance of determinants. So we have now geometric significance of determinants. Okay. So as I have mentioned, we have two conditions, that the equation of a line passing through two given points can be found using determinant. So equation of a line passing through, say, x1 y1, x1 comma y1, and x2 comma y2 is given by the determinant, that is x y1, x1 y1 1, and x2 y2 1, and equate this to 0. Okay. So this will the expansion of this determinant will give us the line of the equation of the line passing through x1 y1 and x2 y2. Okay. Similarly, in the second case, the equation of a plane. Okay. Equation of a plane passing through three given points, plane passing through say x1 comma y1, x2 comma y2, and x3 comma y3 is given as or given by, this will be a fourth order determinant. So this will be like this. So this will be x, y, z, 1. Okay. Since we are talking about 3D, so here the coordinates will also be in 3D. Okay. So this is equation of a plane passing through x1 comma y1 comma z1. This is x2 comma y2 comma z2, and x3 comma y3 comma z3 is given by this. Okay, so x1 y1 y1 z1 1, x2 y2 z2 1, x3 y3 z3 1, and again equate this to 0. Okay. So in this way, the equation of a line in 2D or equation of a plane in 3D can be determined using determinants. Okay. One more application of determinants is there in solving simultaneous equations. Okay. So let us see for a system of equations in three variables. Okay. So that process of the process of solving these equations using determinants is known as Cramer's rule. So we'll now see the Cramer's rule. Okay, so we have now Cramer's rule. So suppose this rule is for finding, or simply let us say for solving simultaneous equations. Okay. Simultaneous equations. So how is it used and implemented? So let us say we have a system of equations with three variables. So say we have a1x plus b1y plus c1z is equal to say k1. Then we have a2x plus b2y plus c2z is k2, and similarly a3x plus b3y plus c3z is k3. Okay. So these are the three equations, and if we need to find the solutions to them, then we can implement the Cramer's rule. And Cramer's rule simply indicates says that first let us write the determinant of coefficients. So say this is m. So m is determinant of coefficients, which will be a1, a2, a3, b1, b2, b3, c1, c2, and c3. Okay. So this is determinant m, and for Cramer's rule to work, this determinant should not be equal to 0. This determinant of coefficient should not be 0. So now all the values are given. So for finding x, simply replace the coefficient of that particular variable which we want to find with the constant values given on right hand side, which means that for x, since x is the first variable, so its coefficients are a1, a2, and a3. So we will replace them with the constant values k1, k2, k3 respectively. and the remaining part of the determinant remains unchanged. Okay, so this will be K1, K2, K3, K3. Okay, and here it will be B1, B2, B3, B2, B3, C1, C2, C3, and then divided by the determinant of coefficients. Okay, so this is like this. Okay, so this gives us the value of x. Similarly, we can find the value of y also. So y will be here a1, a2, a3 will remain unchanged, and coefficients of y will now get replaced by k1, k2, k3. So here k1, k2, k3, and again this is c1, c2, c3. This will remain unchanged. Okay. And again divided by the determinant of coefficients, and similarly z also. Okay, so for z we have a1, a2, a3, b1, b2, b3. Here we will have k1, k2, k3, and we will then divide it by determinant of m. Okay. So in this way, we can solve the simultaneous equations. Okay, so this was for simultaneous equations in 3 variables. Okay, so let us close for now. We will see an example of this application of this Cramer's rule in the next class. Okay, and continue our discussion further. Okay, thank you.